Welcome to module 16, where we are discussing some further examples of conversion sequence. A result is needed now to proceed for the next set of examples. It says that let xn be a sequence of real numbers and let x belongs to R. If an is another sequence of positive real numbers with an tends to 0, and if for some constant C in R, which is greater than 0 also, and capital N belongs to the set of natural numbers, we have this condition xn minus x less than CAN for all n greater than equal to the capital N, then it follows that xn converges to x. This is one type of a dominated convergence theorem where we have to take the help of another sequence an of positive real numbers, and this sequence is converging to 0. Now the proof goes as follows. If epsilon greater than 0 and an tends to 0, there must exist some n naught in the set of natural numbers such that an minus 0 absolute value that should be less than epsilon by c for all n greater than equal to n naught. And this is coming from the definition of a conversion sequence. By the given condition, xn minus x absolute value is less than equal to CAN for all n greater than equal to n. This is a given natural number n. Thus, for all n greater than equal to n star, which is the maximum of n and n naught, both these conditions hold. So this is the first condition and this is the second condition. Both these conditions will hold. That is, xn minus x less than equal to CAN, and an minus 0 less than epsilon by c for all n greater than equal to n star. Combining these two conditions, what we have, xn minus x is less than equal to can is less than equal to can minus 0 is less than equal to c into epsilon by c, and that is equal to epsilon. And this is true for all n greater than equal to n star. Since epsilon being arbitrary, we conclude that xn converges to x, and this completes the proof of this theorem. To let you have a grip on the convergence of the sequence, we will now discuss more examples. The first example is the following. Let xn be 1 by n square plus 1. Then xn converges to 0. How this can be proved? Let epsilon be greater than 0 be given. What we need? We need n in the set of natural numbers such that xn minus 0 is less than epsilon for all n greater than equal to capital N. This is what we want. But here what is xn? Xn is, this is going to be xn less than epsilon for all n greater than equal to n. In fact, what is the value of xn? Xn is 1 by n square plus 1. It's less than epsilon for all n greater than equal to n. And that is 1 by n square plus 1 less than epsilon for all n greater than equal to n. This is what we are going to prove. We have to prove. Now, n is less than equal to n square. This implies n is less than equal to n plus 1 and less than equal to n square plus 1. This implies 1 by n square plus 1 is less than 1 by n. By a similar argument as in the previous examples, we can have now capital N in the set of natural numbers such that 1 by epsilon is less than capital N, and then 1 by n is less than epsilon, and we know because for all n greater than equal to n, we have 1 by n is less than equal to 1 by capital N, and that is less than epsilon. Thus, xn minus 0 is less than epsilon for all n greater than equal to n, and this completes the result. This completes the result. The next example is, take the sequence xn to be 3n plus 2 divided by n plus 1. We will show that xn converges to 3 this time. We adopt a similar procedure. What we have? 3n plus 2 by n plus 1 that can be written as 3n plus 3 minus 1 divided by n plus 1, 3 into n plus 1 minus 1 divided by n plus 1, and this is going to be 3 minus 1 by n plus 1. Now take epsilon greater than 0, a real number. What we need? We need some capital N in the set of natural numbers such that 3n plus 2 by n plus 1 minus 3 less than epsilon for all n greater than equal to n. This is what we need. Now for that we need a condition for 1 by n to be less than epsilon. What we need? We need a condition for 1 by n less than epsilon. This is what we need. This should be for all n greater than equal to n. Now from our earlier discussions, 3n plus 2 divided by n plus 1 minus 3 is ultimately 3 minus 1 by n plus 1 minus 3, and that is going to be my absolute value of minus 1 by n plus 1, and that is 1 by n plus 1, which is less than 1 by n. Now using Archimedean property, we get capital N greater than 0 or capital N in the set of natural numbers. We are using both equivalently. We have xn minus 3 less than epsilon for all n greater than equal to this capital N. Okay, this completes the proof of this result. Now perhaps you can have an idea about how we prove the convergence of some sequences. Basically, if we can find an inequality of the form xn minus x is less than 1 by n, then by using Archimedean property we can immediately get the condition of convergence. So we need Archimedean property afterwards, and we can prove the convergence of the sequence. Following is an example where we also make this condition happen, but you should notice the trick we use for doing that. The next example, we want to show that n plus 1 underscore under root n under root that goes to 0. Now how we proceed here in this case is the following. This expression can be expressed this way also, n plus 1 minus this by dividing by this expression and multiplied by again the same expression. This gives me n plus 1 minus n, and on the denominator it would be n plus 1 under root plus n under root, and this is going to be 1 by n plus 1 plus n under root. Now since n is less than n plus 1, we have square root n is also less than square root n plus 1. And therefore, square root n plus square root n is less than square root n plus square root n plus 1. And it means 2 into square root n is less than square root n plus square root n plus 1. Reversing, we will get 1 by square root n plus 1 plus square root n will be less than 1 by 2 square root n, but which is again less than 1 by square root n. We have arrived at something similar to the earlier examples, but this time it is 1 by square root n instead of 1 by n. For epsilon greater than 0, we have epsilon square greater than 0, and therefore 1 by epsilon square is also greater than 0. Now, by Archimedean principle, Archimedean property applied to this 1 by epsilon square, there exists a capital N in the set of natural numbers such that 1 by epsilon square is less than n. This implies 1 by n is less than epsilon square, but this implies 1 by square root n is less than epsilon. Now, for all n greater than equal to n, 1 by n is less than equal to 1 by n, and therefore 1 by square root n is also less than 1 by square root n, that is less than epsilon. This is true for all n greater than equal to n. Now, from this we have n plus 1 minus, this is the original expression, less than epsilon for all n greater than equal to n. This completes the proof of the result. Next, we show that b to the power n tends to 0 when b is lying between 0 and 1. Now, since 0 is less than b less than 1, 1 by b is greater than 1. Take a to be 1 by b minus 1. Then a is greater than 0. And b is 1 by a plus 1. Thus, b to the power n is 1 by 1 plus a to the power n. Now, expanding this expression, 1 plus a to the power n is equal to 1 plus n a, this is the binomial expansion, n into n minus 1 by 2 a square plus and so and so forth. Now, we have the Bernoulli's inequality that says that 1 plus a to the power n is greater than 1 plus na, and hence 1 by 1 plus a to the power n is less than 1 by 1 plus na. Now, going back to the original expression, we have 0 less than b to the power n is equal to 1 by 1 plus a to the power n, and that is less than 1 by 1 plus Na, that is less than 1 by Na, and that is less than 1 by n. So, ultimately what we have obtained, b to the power n is less than 1 by n, and once this inequality we obtain, immediately by similar argument as we have been already doing, we can say that b to the power n tends to 0, as we have done in the earlier cases also. The last example we are doing here is the convergence of the sequence xn, where xn is given by c to the power 1 by n, and c is something, a positive real number. We will show that xn converges to 1. This is what we want to show. Now, if c is equal to 1, then xn would be, the sequence would be 1, it's a constant sequence of 1s, and definitely xn converges to 1. Let c be greater than 1. Then c to the power 1 by n is equal to 1 plus dn for some dn greater than 0. We can take c to the power 1 by n in this form, and then c equal to 1 plus dn to the power n, and this we can expand as 1 plus n into dn plus n into n minus 1 by 2 dn square, and so on and so forth. But this will further imply that c is greater than equal to 1 plus n into dn. This is Bernoulli's inequality for all n in the set of natural numbers. Now, consequently, c minus 1 is greater than n into dn, implies dn would be less than equal to c minus 1 by n. Therefore, xn minus 1 is the original expression c to the power 1 by n minus 1 is equal to dn, but dn is now less than equal to c minus 1 by n for all n greater than equal to n. Now, take 1 by epsilon into c minus 1 to be greater than 0. Then by Archimedean property, there exists a capital N in the set of natural numbers such that 1 by epsilon into c minus 1 is less than. This is just a trick to get the convergence finally in its desired form. This implies c minus 1 by n less than epsilon for all n greater than equal to n also. And thus, xn minus 1 is less than epsilon for all n greater than equal to n. Let c is lying between 0 and 1, then what happens? Then c to the power 1 by n is equal to 1 by 1 plus some hn, where hn is greater than 0. We can take always such an hn which is greater than 0, so that c to the power 1 by n will be like this. Why? Because c is lying between 0 and 1. Then c is equal to 1 by 1 plus hn to the power n, and this is less than equal to, again using the Bernoulli's inequality, this is less than equal to 1 plus n into hn, and this is less than 1 by n into hn. Then hn is lying between 0 and 1 by nc. This is coming from this expression. We have c to the power 1 by n minus 1 equal to 1 by 1 plus hn minus 1, and that is equal to minus hn after simplification 1 plus hn absolute value, and that is hn 1 plus hn, and that is less than hn, and that is less than 1 by nc by whatever we have obtained. And now ultimately we are getting something which is already we have been discussing many a times, and now based on that, applying Archimedean property, we obtain the required result, and this completes this proof as well as this completes this particular module, where we have been discussing different examples of convergence of sequences, different examples of sequences and their convergence. In the next module, we will be discussing properties of convergence sequences. Various properties are there. We will be discussing those properties of convergence sequences.